This is chapter 3, vectors. In our study of physics, we often need to work with physical quantities that have both numerical and directional properties. Quantities of this nature are known as vector quantities. In this chapter, we're going to be covering coordinate systems, vector and scalar quantities, some properties of vectors, and components of a vector, as well as unit vectors. Chapter 3, Section 1, Coordinate Systems. In this chapter, there are two types of coordinate systems that are described. Cartesian coordinates, which have x and y values that are used to be plotted on a rectangular coordinate system. And then the second type of coordinate system is called polar plane coordinates, or polar coordinates, with an r and a theta value. In polar coordinates, the r value is the distance from the origin to the point having Cartesian coordinates, the x and y value, and the theta is the angle between a fixed axis and a line drawn from the origin to the point. So a continuation of the coordinate systems, there is a relationship between Cartesian and polar coordinates. So Cartesian coordinates, in terms of polar coordinates, we have x equals r cosine theta and y equals r sine theta. And for the polar coordinates, in terms of Cartesian coordinates, we have tan theta equals y over x, and r equals the square root of x squared plus y squared. Now moving on to chapter 3, section 2, vector and scalar quantities. A scalar quantity only has magnitude. Some examples of this is volume, speed, time, and distance, whereas a vector quantity has magnitude and direction, such as displacement, velocity, acceleration, and force. So here are some examples of scalar and vector quantities. Just a quick reminder, a scalar quantity is a value with only a magnitude, and a vector quantity is a value with a magnitude and a direction. So looking at the chart here on the right side, some scalar quantities include mass, length, distance, speed, power, energy, and work. And on the right side of the chart, vector quantities include displacement, velocity, acceleration, force, weight, friction, and momentum. Moving on to chapter 3, section 3, here are some properties of vectors. We're going to be looking at the equality of two vectors, adding vectors together, the negative of a vector, subtracting vectors from each other, as well as multiplying a vector by a scalar. Equality of two vectors. Two vectors may be defined as equal if and only if they have the same magnitude and if they point in the same direction. So looking at the graphic on the right here, vector A is equal to vector B only if the magnitude of A is equal to the magnitude of B, and if the direction of vector A is the same direction as vector B. So here we're going to be talking about adding vectors. So to add two vectors together, first you need to draw the first vector, in this case vector A. Then you need to draw the second vector. Here we are, the vector B, with its tail starting from the tip of the first vector, which was vector A. This creates a resultant vector, vector C, which is the vector drawn from the tail of vector A to the tip of vector B. So we're moving on to look at the negative of a vector. The negative of a vector, in this case vector A, is defined as the vector that when added to vector A gives 0 for the vector sum. So in this case, we have vector A and vector negative A when added to A is 0. So vectors A and negative A have the same magnitude, but they point in opposite directions. So continuing on, we're going to be looking at subtracting vectors. So to subtract a vector from another vector, first you need to draw the first vector, vector u. Then you need to draw the second vector, which is negative v in this case, with its tail starting from the tip of the first vector u. So if you look at the graphic on the right, you're going to be first drawing the blue vector u, then drawing the red negative vector v, and then the resultant vector in this case is going to be vector u minus vector v. The last property of vectors that we're going to be talking about today is vector multiplication with a scalar. So in this example, vector A is multiplied by a positive scalar 3, which results in a product of 3 vector A. So 3 vector A has the same direction as vector A, but now it has a magnitude of 3A, as shown in the graphic on the right. So chapter 3, section 4, vector components and unit vectors. A vector's components are used to retain high accuracy when adding or subtracting vectors from each other. So in this example on the right, vector A can be expressed as the sum of 2 other component vectors, a sub x and a sub y. So last but not least, a unit vector is a dimensionless vector having a magnitude of exactly 1. So on the graphic here, unit vectors are used to specify a given direction. So I hat, j hat, and k hat. I hat is the x direction, j hat is the y direction, and k hat is the z direction. So if you look at the little example I have, the vector A can be broken down into a sub x plus a sub y plus a sub z. And if you even look below that, a sub x is described as a sub x I hat, a sub y is expressed as a sub y j hat, and a sub z is expressed as a sub z k hat. Okay, and that's a wrap of chapter 3 on vectors.